When we have addition or subtraction, that means we're like separating this into two pieces and finding the antiderivative of each piece separately. So if I look at that 2e to the 3t and I'm looking for the antiderivative, because it's an exponential, I know that I'm going to end up with exactly that same thing back. But because we're finding the antiderivative, I'm going to have to divide by -3. And we can either think about that as just a rule that we're memorizing, that when we find the antiderivative of something that looks like e to the kt, then my antiderivative is 1 over k e to the kt plus some sort of constant. And that's just one of those antiderivative rules that I mentioned are on page 345 in a nice little chart. Now that's not the entire antiderivative because we still have to deal with that -1 piece. And because this was given to us as dr dt, that means that when I'm looking for the antiderivative for the -1, or I'm thinking about which function has a derivative of -1, I want to make sure that the variable I'm using, the letter I'm using is t. So this is going to look like -t plus some sort of constant. Don't have to, but if we want to, we can rewrite this. That 2 over -3, I can write as a -2/3 e to the -3t minus a t plus c. So that was kind of like step 1. Step 2 is that I'm going to use that initial condition or the additional information I was given. So here, notation-wise, this is telling me that when t is equal to 0, r should be equal to 5/3. So if I take that 5/3 and I plug it in for r, and I take 0 and plug that in for t, and end up with -2/3 e to the 0 minus 0 plus that constant. And then this one, we're just going to have to remember, anytime I'm looking at e to the 0, that is secretly equal to 1. Solving for c means I'm going to add that 2/3 to the other side. 5/3 plus 2/3, I'm looking at 7/3 is equal to c. So we've done all the work, but our final answer is that we're going to rewrite what r is, but plugging in that c. So my final answer here is going to look like r of t is equal to -2/3 e to the -3t minus t plus 7/3. Today we're moving into section 5.1, which means we're going to talk a little bit about sigma notation. Now, for those of you that have seen sigma notation before, this is just a way to summarize when I'm adding up a bunch of little things, which is kind of what we're about to do in section 5.2. We're going to first get some underlying kind of shortcuts and learn how to work with the sigma notation. So here I have one example. This letter is a capital Greek letter sigma, and sigma means we're going to take a summation. We're going to be adding things together. That I minus 5 part, that's telling me what's the thing I'm going to be adding together a bunch. And the I equals 1 at the bottom tells me where to start. The 6 tells me where to stop. So here's what this would look like if I expanded this out. I'm going to start at the I equals 1 and take that 1 and plug it in to the expression that we're going to be adding up. So in this case, that's going to look like 1 plus 5. Then I'm going to add that. That's what my sigma notation is telling me to do. And increment by 1 to now be at I equals 2. So I'm going to plug in 2 plus 5. And I'm going to keep going, incrementing always by 1. So 1 plus 5, 2 plus 5, 3 plus 5, 4 plus 5, 5 plus 5, and finally 6 plus 5, because this told me to stop at 6. Now I can pull out a calculator and punch in numbers and add all of this up. But it's going to be really helpful for us with what we're going to do next, not next today, but probably next week, to be able to have some rules to get through this addition faster. So one of the first things that we're going to do is look at regrouping this. Now, each of these terms has a +5 on it. So I could take all of those +5s and push them together over here. So I'd have 1, 2, 3, 4, 5, 6 of those 5s. 5 plus 5 plus 5 plus 5 plus 5 plus 5. And then the parts that are left, the 1, 2, 3, 4, 5, 6, I could group those together to say 1 plus 2 plus 3 plus 4 plus 5 plus 6. Now, even just writing all of that out took a bunch of time, but really what I wanted to show you is that if my expression has addition or subtraction inside of it, that we can actually break that up as separate pieces, just like we did here. So this would really be me writing I from I equals 1 to 6 plus, and this one's a little bit tricky, but the expression each time was just 5. So there isn't anywhere for us to plug in the I, but we'd be going from 1 to 6. So when we have addition between pieces in our expression and we're taking the sum, we can break those apart. Now this next part, we're getting into the shortcuts. Well, here we know that when we expanded this out, we had 1, 2, 3, 4, 5, 6 sets of 5, which means this, if we evaluated it, would be 6 times 5. This one, some clever mathematicians came up with a shortcut for also. And here is what they did. Someone looked at this and said, well, 1 plus 6 is equal to 7. 2 plus 5 is equal to 7. And 3 plus 4 is also equal to 7. That means that I have 3 pairs that add to 7. So the shortcut here is this is 3 times 7. Now if we write those shortcuts out a little more generically, we're going to come up with 2 of the first formulas for this section. If I take the sum of I from I equals 1 to some number n, we're going to be able to do this same thing where I pair the first term plus the last term. So that's 1 plus n. And I multiply that by the number of pairs we had. Well, if I had 6 terms, then that turns into 1, 2, 3 pairs. And if I have n terms, that turns into n over 2 pairs. This formula in our textbook is usually written as n times n plus 1 all over 2. This one over here, I could say we were going from 1 to a generic number of a constant. In our case, the constant was 5. But the formula for this, our shortcut version, is that we end up with n times 5, or n times c. I am reasonably sure that these formulas would be given to you on a short test, and for sure they're given to you on the Weber homework, but I just wanted to say we kind of use them enough. I think these 2 are probably worth memorizing. And maybe you can imagine that some clever mathematicians started writing all of the square numbers out and did some cool things. It's actually a whole lot of algebra to get to here. And I'm happy to go through that proof in office hours sometime. I'm also happy to record a separate video walking through that proof, but I don't really think it's worth our time in co-class right now. It's more important that we're able to use it. So for example, if I asked you to compute, or if there was a web work question that was asking you to compute something like the sum from 1 to 15 of I squared, this formula says rather than grabbing your calculator and doing 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, all the way up to 15 squared, we can use this formula where that 15 is my n. So this would look like 15 times 15 plus 1 times 2 times 15. So now I'm at 30 plus 1 all over 6. And for the next 2 minutes, even if you've taken calculus before and you've seen some second quarter calculus stuff, pretend you haven't. Prepare to be amazed. No, not really. It's not that amazing. Just pretend you haven't done the calculus stuff yet. So suppose that I wanted to find the area from, I'm going to call that x equals 0, and I'm going to call this over here x equals 4. And I wanted to find the area in there. Well, back when you were a little kid, or maybe more recently than that, you probably knew how to find areas of things like triangles and rectangles and maybe even a trapezoid, a circle, a semicircle. This is none of those things. So clever mathematician, lazy mathematician, says, well, if I want to find the area in there, what if I just fake it by finding the areas of some rectangles? So mathematician comes in here and says, well, it's not going to be exactly the area I want, but if I were to cut this in half and just think about approximating that with some rectangles, and I found the area of this rectangle, and I found the area of this rectangle, it wouldn't be a perfect match for the area I wanted, but it'd be fast to calculate, and it maybe wouldn't be terrible. By the way, if I wanted to find the areas of those two rectangles, cutting this in half right here would mean that I was exactly at x equals 2. And for the rectangles that I drew, I used right-hand endpoints, because for this rectangle, I drew my height from the right-hand side of each rectangle. I drew this height in from the right-hand side. So that means if I wanted to approximate this area, I would get that area by doing the area of this first rectangle. So my base is 2. And to get my height, I'd be using the height from the right-hand x value. So when I take that x equals 2 and plug it into the formula, the height of that first rectangle would look like 2 squared plus 1. Then I would take the area of that second rectangle. My base is also 2. And to get my height, I'm going to use the x value on the right-hand side of that rectangle. So I'm going to end up with 4 squared plus 1. We're going to do more with this on Friday and really kind of for the next 3 weeks. But where this is going and how this is connecting back to the summation notation thing is, can we all agree that the areas of my two rectangles are not really that close to the area I wanted? Is it an overestimate or an underestimate? Yeah, it's going to be an overestimate if I do that. So mathematicians, they're lazy. They like finding shortcuts. Maybe lazy is the wrong word. They want to be efficient with their time. But they also want to be precise. So maybe using 2 rectangles isn't super precise, but what if we put 4 rectangles in there? And I did that same thing where I used right-hand endpoints to find each of the heights for my rectangles. Well, now instead of adding 2 things together, I'm going to be adding 4 things together. The base of each of my rectangles now is only 1, right? So when I find that first area, I'd have a base of 1, and I'd get my height by plugging 1 into the formula. And then for my second rectangle, I'd have a base of 1, and I'd get my height by plugging 2 into the formula. And then 3, and then 4. Now, hopefully, maybe you're starting to see that this garbage over here can also be written using sigma notation. So adding up all of these rectangles, I could write that as, well, all of these have this 1 in common right now. And then if I look at where we're splitting at the summation, I look at where each of those splits is happening, and I turn that into a sigma notation. What we're doing each time is taking the number we've plugged in, squaring it, and adding 1. So I'm taking the number we plugged in, squaring it, and adding 1. We started at I equals 1, and we took 4 rectangles. So the reason that you're getting some practice with the sigma notation is that it's going to give us sort of a shortcut for calculating when we're adding up a whole bunch of rectangles. I promise we will get more practice with this, but I also want to do an example that involves distance. So this thing we were talking about area, and I think that's a little bit more tangible. But some of the other examples in section 5.1, we're not given a graph, we're actually just given a chart of things. So I'm going to erase stuff. Going once, going twice, take a screenshot. Okay. So I want to look at an example from the book really quick. And in case you want to play along, sorry, scrolling forever. I wanted to look at problem 7, and hopefully you've given it a shot already, but in case you haven't, we're going to take a look at problem 7 now. And in problem 7, we are told that a runner's speed increased during a race. And I don't know, maybe they were like wearing a cool Garmin or Fitbit thing. And so they got some data that tracked the time, meaning how long they had been running, and what their velocity was in feet per second at that moment. Well, at the start of the race, they weren't moving yet. So it makes sense that the velocity was 0. 5 seconds later, or sorry, half a second later, the velocity was 6.2. 1 second into the race, the velocity registered as 10.8. Another half a second into the race, it registered as 14.9. And I'm just going to go one more. 2 seconds into the race, this was 18.1 feet per second. There's more data than that in the problem, but in the interest of time, I'm just going to use these 4 data points. So I want to estimate how far they ran in the first 2 seconds. Well, one way that we can do this is to say, well, and this is actually the truth about data collection. Nothing is continuous. We're not actually collecting data points continuously, we have specific times that we're taking these data. So we have to make an estimate of kind of what happened in between. Well, one of the ways that we can do that is to assume that for this time interval, for that first half a second, one choice we can make is to assume that we'll just keep the velocity at 0 for that whole half a second. Another option we have is to assume that the velocity was 6.2 seconds for that entire half a second. Since distance is equal to rate times time, we can get this estimate of the distance, and we can give a lower bound estimate, assuming that we're always going to choose the slowest velocity, and an upper bound estimate, assuming we're always going to choose the fastest velocity on each interval. So here I have 1, 2, 3, 4 time intervals that are each an interval of 0.5 seconds. So as a lower bound, I'm going to use this rate times time thing. And in that first interval, I'll assume the slower rate, the 0 feet per second. So I'd have 0 feet per second for the first half second. In the second interval, I'll continue to use the lower rate. So I'll pretend that she was running at 6.2 feet per second for that next half second. And then in the next increment, again, I'm choosing that lower bound, so that 10.8 for half a second. And in that last interval, I'll also choose the lower, the 14.9 times 0.5. Now we could do this all over again, assuming an upper bound. And then for each of those velocities or rates, we would swap each of these out for the larger value in each time interval. And we call those a lower bound and an upper bound, or sometimes we refer to those as left-hand endpoints, right-hand endpoints. In this case, the left and right makes less sense to me just because we're not exactly looking at a graph. We've got a table of values. So I think about it as the lower bound choosing the lowest value in each interval, and the upper bound choosing the largest value in each interval.